So yesterday, we talked about reviewing scalars and vectors. Okay, scalar quantities are things that only have magnitude but no direction, speed, distance, mass, work, energy, okay, time. And then there are vector quantities. Vector quantities have magnitude and direction, velocity, displacement, acceleration, force. Okay, those kind of things are all vector quantities. What I want to do today is kind of go over some vector versus scalar types of questions, because we kind of solve them a little bit differently, because we have to take into account things for vector that we don't have to take into account for scalar. Okay, quickly review the use of v equals d over t and understand what that formula really means, or what it can mean because it has multiple meanings. Okay, so first thing is, if I'm using any formula and I need to change it, I need to manipulate it, okay, then I need to make sure I follow the 3 rules of algebra. All right? If I want to move something, I do the opposite. Okay, so if I'm multiplying, I would divide. If I'm dividing, I would multiply. Adding, I would subtract. Okay, what I do to one side, I have to do to the other. Okay, and the 3rd rule of algebra is move what's not attached to what I'm looking for first. Okay, we actually don't need that rule for v equals d over t, but we would need it for other types of formulas that we would use. Okay, so if I want to manipulate v equals d over t, let's say I want to solve for d. What do I have to do?
Multiply t on one side and t times b.
Right, multiply both sides by t. Okay, if I'm going to move it, I have to multiply. What I do to one side, I do to the other. Okay, so what essentially ends up happening, okay, is t comes over here. Now I have t times v equals d. Everybody all right with that? Okay. What if I want to solve for t?
You would divide the d on both sides.
Okay. If I do that, so I divide both sides by d. What's d divided by d? 1. Is 1 over t the same as t? It is not. Okay, and that's a very common thing. That's why I wasn't trying to say champagne. Okay, but that's a very common thing that people do. They look at that and they go, I just have to get it by itself, forgetting that I can't 1 over something is not the same as that thing. That's like saying 2 is the same as 1/2, right? And they're obviously not the same.
I would multiply by t to get it from the bottom, and then divide by both.
Exactly. Okay, so if I want to get d by, or t by itself, I first need to make sure it's on the top of my equation by multiplying it over here. And then I take v and divide it over to this side. And now I'm solving for t instead of 1 over t. Okay, that makes sense to everybody? We can only solve for something when it's on the top of an equation. So if it isn't there, we need to move it there somehow. Okay. All right. The other thing we have to realize about v equals d over t is that, whoops, it doesn't mean that velocity is displacement over time or speed is displacement over time. It actually means this. Average velocity is total displacement over total time. Okay? Most of the time we don't write the total in because we're only using it for one thing. But if I have a question that describes a trip that an object makes that has several parts, and then says to me, calculate the average velocity over the whole trip, in order to do that, I need to know the total displacement and the total time. Okay? That is, I need to figure out what was the displacement in part 1, what was the displacement in part 2, what was the time in both parts, so that I can get the total. Okay? Everyone follow me there? Because there's a mistake that people often make, and it is that when they're told, find the average velocity, they're like, okay, I'll find the velocity in 1 and 2, and I'll add them together and divide by 2, because that's how you calculate averages. Which is how you calculate averages if all the things you're adding together are equal parts of the whole. Okay? Here's what I mean by that. If I'm going to calculate a class average on a quiz or a test, every one of you is an equal part of the class. So all of your scores represent an equal amount of the total. Are you with me there? Okay. That's not the case for v equals d over t. let's say this trip is a trip to Edmonton. I drive from Okotoks to Leduc, which is like 10 minutes south of Edmonton, okay, at 120. I get to Leduc and there's a bunch of highway construction. For the last 10 kilometers of my 320 kilometer trip, I have to travel 50 kilometers per hour. So, am I going to go 50 plus 120? I don't know why I wrote 1/2. Plus 120 over 2 to get the average? No. Okay? Absolutely not. I only went 50 kilometers per hour for 10 of 320 kilometers. My average velocity is going to be like 112. Okay? Not whatever 170 divided by 2 would be. Okay? Certainly not 112. Okay? I went 120 for almost the whole trip. My average is much closer to 120 than it is to 50. If I do it this way, it says my average is exactly halfway between the two, which it totally wasn't. Okay? Everyone follow me on that? That's why we have to go total displacement over total time. That will reflect that I did a lot of the trip at this speed and much less of the trip at this speed. Okay? Total displacement over total time weights the average in favor of whatever part is bigger. Okay? Everybody all right with that idea? Okay? The same is true for speed. Okay? If I just took the little arrow off of here, this would be average speed equals total distance divided by total time, and that's how we use it if we're dealing with a multi-part trip. Okay? We would use just V equals D over T for individual parts of the trip, but when we're talking about the total, okay, or the whole trip, then we have to use it this way. Everybody all right with that? All right. So here's a question that's just like the one I kind of proposed to you about the trip to Edmonton. Okay? I want you guys to write that one down, and given what I just explained, see if you can solve that. Okay? Then we'll walk through it together. All right, so if I'm going to solve a two-part question, I got to write down my givens kind of organized by section. Okay, so it tells me that in part 1, or the first part of the trip, it travels at 4 meters per second north. So it gives me the velocity for part 1, and it gives me the time for part 1, 12.5 seconds. Okay, then it tells me that in part 2, it turns around, okay, and travels 26 meters south. So they give me the displacement there. Okay, and it does that at a velocity of 16 meters per second, which would also be south. It doesn't outright say that, but obviously velocity and displacement have to be in the same direction. Okay. Now it's asking me, what's the average velocity and what's the average speed? Okay, so I'd have kind of a third column here that would be my totals. Because if I'm going to find average velocity, I need the total displacement and the total time. Problem is, I don't have displacement for part 1, and I don't have time for part 2. Can I get them? Yes. Okay, and so that's what we have to do first. I have V and T for part 1, so I can solve for D. All right, so D will equal V times T. Okay, do I need to show you guys the manipulation, or are you good with that? Okay. So we got our 4 meters per second, okay, times 12.5 seconds, should give me 50, right? 50 meters north. I shouldn't do math in my head, did I do that right? Okay. All right, so I got 50 meters north is my displacement for part 1. I got to do the same thing in part 2, but instead of solve for displacement, I've got to solve for time. Okay, so time equals D over V. Okay, so that'll be our 26 meters divided by 16 meters per second. Okay, so we're going to have 26 divided by 16. So that part only takes 1.625 seconds. Okay, so I have the time for both parts, and now I have the displacement for both parts. So can I figure out what the total displacement and total time are? Okay. So my total displacement is that I went 50 meters north and then 26 meters south. So I'm going to have positive 50 plus negative 26. Okay, or minus 26, whichever way you want to look at it. I'm assigning negative to south and positive to north here. All right, so my total displacement is going to be 24 meters north. Everybody all right with that? Okay. And my total time is going to be 12 and a half plus 1.625, which is what, 14.125? Seconds. Can I calculate my average velocity? Okay. Average velocity is total displacement over total time. So that'll be 24 meters north divided by 14.125 seconds. All right, so we're looking at 1.7 meters per second. North. Okay, obviously velocity is a vector quantity. The other part of that question was calculate the average speed. What do I need to do in order to get that? Average speed is?
It's distance over time.
Right, it's total distance divided by total time. It's dealing with the scalar view of this trip. Okay? So instead of calculating displacement where north and south matter, I need to calculate distance, which is scalar. So instead of subtracting the 26, now I'm going to add it. Or I'm just going to add, I'm going to make it not negative. Okay? So I'm going to have a total distance traveled now of 76 meters. Okay? That's how far we went. It's not how much our position changed, but it's how far we went in doing this. Okay? Is the total time any different? Total time is the same. Okay, so V equals then 76 over 14.125. Okay, and we're looking at 5.4 meters per second. Okay, everybody all right with a two-part question? And that's how they all work. Okay, I can give you a five-part question. It would be the same thing. You just have to calculate D and T for the different sections and then do the totals at the end. Okay. So the big thing there that we're trying to kind of illustrate with that question is average means total over total. Okay, whatever you've got for the entire trip in question divided by the total time. Okay, everybody all right with that? Rather than adding sections together and dividing by the number of sections, we don't do that in physics. All right. So what I would like you guys to do, I've got some really easy V equals D over T ones here. Okay, just want you to try those for a little bit just to kind of get the hang of it. They are in the digital workbook. So okay, so on page 2 here of the Unit 1 digital workbook, I would like you guys to do, let's say, number 6. Number 7 is just like what we just did. And number 8 you can do without a graph. So you can just solve that one kind of the way we did there. So let's have you try those 3. 8's probably the trickiest. Okay, it's got 3 parts, and there's kind of it's a little bit more involved than the one we just did, but I think you guys can handle it. So let's have you do those 3. You may. Okay, so quickly for number 6, if I don't know why I spelled further that way. It's terrible. Further. Okay, so if we've got these 2 really, really slow animals, okay, and we want to figure out which one's going to go the furthest. Okay, we just have to solve for their distance traveled. Okay, so if we have the sloth, okay, we know that the sloth can move at a speed of 0.037 meters per second, okay, and we know that the tortoise, okay, can move at 0.076 meters per second. Okay, they're both going to walk for 12 minutes. What's the problem with me giving you the time in minutes?
You have to convert it to seconds.
Yeah, I got to convert it to seconds. Okay, I can't have meters per second and minutes. My units have to match. So either I've got to change the speed to meters per minute, or I've got to change the time from minutes to seconds, which is easier. Okay, so 12 times 60 is going to be what? 720 seconds. Oh, same amount of time for both. Okay, all we have to do is then go d equals v times t. Okay, d equals v times t for both. So that'll be our 0.037 times 720, okay, and 0.076 times 720. Okay, so if we're looking at that, we should have that the tortoise is going to go 28 meters further in those 12 minutes. And we only find that by subtracting them after we've done the calculation. So we got our 0.076 times 720 gives us that, minus 0.037 times 720. Okay, 28 meters. Everybody all right with that? Okay, and then go down number 7. Okay, let's go over that one too then. Okay, so number 7 is much like the garbage truck question that we did together here a few minutes ago. Okay, we've got the first part, okay, and this is simplified greatly because obviously when you jump out of an airplane, you don't fall at a constant velocity. Okay, you accelerate until you reach terminal velocity, and then you fall at that velocity until you either open your parachute or something awful happens. Okay, so we have, okay, part 1, which we're going to call the free fall part. And in that part, they fall 625 meters in 15 seconds. Okay, and then we have the other part here where they fall 356 meters in 142 seconds. Right, so this one's actually much easier than the garbage truck question because it gave you D and T for both. Okay, you didn't even have to go and do any intermediate calculations. You could go straight to our totals. Okay, our total displacement, okay, 981 meters, and our total time is 157 seconds. Okay, so our average speed would be 981 divided by 157, okay, which is going to be 6.2 meters per second down. Okay, so they obviously fall a lot slower with the parachute open, okay, than they did in the first part where they fell a long way in a very short period of time. Okay. And people have done number 8. Okay, we'll give you a few more minutes on number 8, okay, and then we'll go over that one. The correct answer, by the way, is 34 kilometers per hour north. I think it was on the sheet. So for this one, there's 3 parts, plus the total. Okay, so we're just going to split it up like that and get our givens all written in. Okay, so the car makes a 60-kilometer trip with an average velocity of 40 kilometers per hour north. Okay, so that's the stuff for the totals. They gave me that in the first line. Okay, so I know that the average velocity is 40 kilometers per hour north. Okay, and I know that the total displacement over the whole trip is 60 kilometers north. Okay, so I know those 2 things right off the bat. The trip consists of 3 parts. The car moves at a constant velocity of 25 kilometers per hour due north for the first 15 kilometers. All right, so 25 kilometers per hour north, 15 kilometers north. Okay. and then 62 kilometers per hour due north for the next 32 kilometers. Okay, with what velocity does the car travel for the last 13 kilometer segment of the trip? All right, so we know that. We know the displacement for part 3. Okay, so that's all the information that we have. They want the average velocity here. What don't I have for part 3 that I need? Time. Okay. So I need the time for part 3. There's no way for me to get it with the information from part 3 because I don't have enough. Okay? But I know how far and how fast the whole trip is taken at. Can I find the time for the whole trip? Because I've got D and V for the whole trip. Okay, so I'm going to find the total time here by simply going D over V. 60 over 40, which should be 1.5, right? Okay, the whole trip takes 1.5 hours. Can I find out how long the first 2 parts take? Would that give me a way to figure out how long part 3 takes? Okay. So time for this part is going to be 15 over 25. Okay, so that part takes 0.6 hours. Okay, and for this part, 32 over 62. Okay, so 0.52 or 0.516 hours. Okay, so I know the total and I know 2 out of the 3 parts, so I can find the time here. The time here will be 1.5 minus 0.6 minus 0.15, or 0.516, sorry. Okay, so 1.5 minus 0.6 minus our answer from the last one. All right, so that last part takes 0.3838 hours. Now I should be able to find out what my velocity is for the last part, because now I have the time. Okay. Okay, so now that I've got that, okay, now I can just go V equals D over T, 13 for that number. All right, so in the last part, 34 kilometers per hour. Okay. Now, would it give you one like that on a test? No. Why would I make you take 8 minutes to do the same calculation 3 times? It's not an effective use of time. It's just an exercise to kind of get everything going again after a break from Science 10. Okay? Quite frankly, a question like that is probably beneath you, okay, at this point, but it's good to just kind of get it back into flow. All right. Questions on that? You guys good with that? Okay. Want to do a little bit of kind of reviewing here, okay, in terms of like our graphing stuff, okay, from Science 10. Okay, so position versus time graphs, velocity versus time graphs. Okay, because my plan is on Monday to do our first lab on position versus time graphs. Okay, so we're gonna kind of go through that stuff just to kind of refresh our memory on how that stuff works. And then once we're done that lab, then we're going to go into vector addition. So we'll start the trigonometry part, okay, of the unit, and then we'll do acceleration after that. Okay. So let's have a look at that. All right, so we're not going to really see anything different in Physics 20 to do with position versus time and velocity versus time graphs from what you learned in Science 10. We're still going to do position versus time and velocity versus time graphs. I'm going to ask you to calculate kind of similar things from both. What we want to do differently is look more at how do I figure out what's on this graph, as opposed to I memorized in grade 10 that I get this from this graph by doing this, and I memorized this part and I memorized that. Because In the end, that's what a lot of people do. Okay, it gets them through the physics unit in Science 10, and then they never think about physics again. Okay, and then they realize, oh, I'm going to take Physics 20, and then we have to look at, all right, it's not an effective thing for us to do to memorize how to calculate something from every graph we encounter, because in Physics 30, you could be looking at 36 graphs by the end of Physics 30. Okay, it will be very hard for you to memorize what everything is on each one of those graphs. Okay, the better approach is to learn how to look at a graph and analyze it. Okay, that is go, all right, I have this graph and has this information on it. How can I get what I'm looking for? As opposed to, I memorized the slope is the velocity on this graph, and the area under the line on this graph is the displacement, and then you start getting them mixed up. Okay, and then you're calculating the wrong things. So we want you to kind of have the skill set of being able to analyze any graph on the fly. Okay, so that's what we're going to kind of look at here. So understand what information can be read from the two graphs we're going to go over. Okay, understand that graphs and equations from kinematics show the same information in different ways. So this whole thing that we've been doing this morning about average velocity being total displacement over total time, average speed being total distance over total time, that comes into play here when we're analyzing a graph. Okay, we can do exactly the same thing with a graph. Okay, it's just looking at it from a different perspective. Okay, so if I've got this position versus time graph, okay, a position versus time graph tells me where an object is as a function of time. Okay, so in this particular graph that we're seeing here, okay, at time 0.1 hours, okay, it is at a position of negative 18 kilometers. Okay, so it's telling me where it is. Now, when I look at this graph, okay, the first part of this graph is just a diagonal line. So from here to the dot, okay? So from here to the dot is just a straight diagonal line. If this graph is showing me position as a function of time, in this part of the graph, the object is changing its position. Would you agree? Okay? That's one of the first things we need to be able to do when we look at a graph, is look at it and go, what's happening? What is this graph showing me? Okay? This part of the graph is showing me an object whose position is changing. That would be the simplest analysis. Okay? Now, in what way is the position changing? If this line is straight, and it is, okay, not after it's curved, but to here at least it's straight. Okay? Does that mean the position is changing at a constant rate? It does. Okay? It basically means that every time interval, every equal time interval, I did a terrible job of drawing that, okay, but every equal time interval, the position, which would be this part, changes by the same amount. Okay? If my position changes by the same amount every time interval, then I'm traveling at a constant velocity. Okay? That's graph analysis. Okay? I don't need to memorize that. I can look at the graph and go, oh yeah, it's whatever it is changing at a constant rate. What's on this graph? Oh, position and time. When position changes at a constant rate, that's a constant velocity. Okay? This graph could be of anything. A straight line on any graph means y is changing at a constant rate as a function of x. Okay? And that's kind of the things we need to be able to analyze from a graph. Now, this next part, it says, is decelerating. Okay, so it kind of spoils it for us. But okay, how do we know that in this part of the graph, the object is decelerating? How can I look at this shape and know that that means that it's slowing down?
The time for it to reach its next position is lengthening. I think it needs more time to get to the next position.
Yes. Yeah. Or it doesn't go as far in equal time intervals. Yeah, same thing. Right. Okay. So what we're saying here is if we have those equal time intervals, okay, so this, now an equal time interval, okay, notice how these lines, the vertical lines, are getting shorter and shorter. Okay, every equal time interval, I don't go as far as I did, okay, the time before. Okay? That means that I'm slowing down. Right? The other part of this is I can say, all right, the line here was showing me something traveling at a constant velocity, and it was straight. Now, it's not straight. Well, that means that the rate at which it's moving is changing, because now it's no longer straight. Everybody all right with that? Okay, now, I know it's slowing down because of this little thing here that we drew, but the other way I can look at it is, well, eventually, the line is flat. If the line's flat, then the position's not changing. That means the object is stopped. So here it was moving, and here it stopped. Well, in between, it must be slowing down. Stuff doesn't stop instantaneously. Okay? So again, that's just me looking at a graph and going, what is this graph telling me, as opposed to memorizing what a shape on a graph means. Okay? I can do that more easily, okay, than I can to try and memorize what 36 different graphs are. All right, now for this part of the graph, it tells us it's accelerating. Okay, is it similar reasoning to this? Yeah. Okay, every time interval. If I'm looking at equal time intervals here, so in this 1/10 of a second, we only went that far, or 1/10 of an hour, sorry. In this 1/10 of an hour, we went further. In this 1/10 of an hour, further. We must be going faster. Okay? That's just, again, analyzing the graph. All right. So on a test, I could give you a multiple choice question as a picture of a graph and ask you what's going on in part B of the graph. And you would have to look at it and go, okay, this is a position time graph. So you know, the line looks like this, so that means position is changing over time. It's moving at a constant velocity. Okay, and then pick A, B, C, or D. That's how I would test them. Make sense? All right, slope calculations. In Science 10, hopefully, okay, you learned how to calculate slope. Probably not this way. Okay, you probably didn't do rise over run. If you did, that's fine. It's just not as useful as using y equals mx plus b. Okay? In Math 10, you should have done both. How many people have used y equals mx plus b? All right, so we use this a lot. Okay, because we have a lot of graphs that are going to be linear functions. Okay, and that's the function for a linear graph. So y represents any y value. What does m represent? Slope, okay? X represents any x value. What does b represent? The y-intercept. So what is the value of y when x is 0? In other words, the initial y value. That could be initial position or initial velocity, depending on what kind of graph you have. Okay? So on this graph here, this is a position versus time graph. Okay? If I find the slope of this line, okay, so let's say I manipulate so that I'm solving for m. That'll be y minus b over x. So in case you don't follow my manipulation here, okay, our 3 rules of algebra, all 3 come into play with this one. I'm looking for m, so I need to move both b and x. Okay, what's not attached to m? B. So I would move b first. That's rule 3. Move what's not attached first. All right, I'm adding b on this side. So to move it, I would subtract b. So I would have y minus b equals m times x. To get m by itself, divide both sides by x. Okay? All right, so that works no matter what kind of graph I'm dealing with. That will calculate the slope, y minus b over x, which is that formula. It's the change in y, rise, divided by the change in x, the run. Okay, so that's where that formula comes from. It's actually just using y equals mx plus b. Now, on this graph, what is the slope going to represent? When I calculate the slope, what am I actually calculating?
The rate of change.
Okay, in the rate of change of what on this particular graph? Yeah, well, actually, in this case, it would be velocity, but it could also be speed. Yeah, okay. So on this graph here, the slope is going to represent velocity. Okay, and it's not a matter of memorizing it. It's a matter of looking at this and going, all right, on the y-axis is position. Okay, so when I say y minus b, what I'm really doing is going final position minus initial position, right? This value here would be my final position. This value here, b, is my initial position. Okay, and what's on the x-axis? Time. What does that calculate? Yes, but in this case, final position minus initial position is displacement. What is displacement divided by time? Velocity. Okay? The slope of the line on this graph represents velocity. Okay? It's not something I have to memorize, it's something I can figure out. Now, we're only going to use two kinds of graphs, you're probably just going to remember that. But this is the process we want you to go through when you're encountering a new graph. Okay? If you encounter a graph you've never seen before, you should be able to go through this and figure out what does the slope of that one represent. Okay? No matter what kind of graph it is, by using that process. So let's say, instead of this graph, I have this graph instead. Okay? So now I have a velocity versus time graph. Okay? Okay, what's on my y-axis? Velocity. Okay, velocity is on my y-axis. So if I go y minus b, what I'm really doing is taking my initial velocity and my final velocity. Right? That's what those two y values would be. This would be b. This would be y. Okay? So I'm really going VF minus VI over time. What does that calculate? Close. Acceleration. Okay? So I can calculate acceleration from this graph by calculating the slope. Okay? And in fact, is this a formula that you used last year in Science 10? That's where that formula comes from. Okay? A lot of the formulas we use are derived from graphs. Okay? They actually represent the slope of the line, or sometimes they represent the area under the line. Okay? It all depends on what kind of graph we're dealing with. Right? So that's kind of the process we want you to be able to go through, is to be able to look at a graph and go, all right, a question wants me to take this graph and calculate this thing. How can I do that without having to memorize it? The slope of this graph is acceleration, and the slope of this graph is velocity, and the area under the line on this graph is displacement. The area under this line doesn't mean anything, okay? Because you got some graphs where it's like that. Okay? I have people who do this all the time. They remember that they have to calculate the area under the line on a graph because it calculates something, but they don't remember which graph. So they calculate the area under the line of this graph. Okay? If I calculate the area underneath this line, that's base, which is seconds, times the height, which is meters. I don't know what meter seconds are. I don't know what that measures. Nothing. But people will calculate that and tell me it's the displacement. I'm like, really? It's not. Okay? It would have been if it was this graph, but you memorized it wrong. Okay? That's the danger of the memorization. Okay? Is that we sometimes apply it wrong. Okay? You have to memorize so many things we forget which thing it goes with. Okay? But if we analyze each graph separately, okay, we're better able to figure that stuff out. All right. So this is a position versus time graph. It's obviously not a single linear function, so we won't be using y equals mx plus b for this graph. Okay? But could I still ask you to calculate for me the total displacement? What is the total displacement? 0. Okay, so here's how we do that. Okay, we know that total displacement is final position minus initial position. Everybody okay with that idea? And that's what this graph is showing me, is the position of the object. My final position is 0. Oh, and so is my initial position. So, did it go anywhere? I mean, I did, but I came back to where I started. Okay. In what part of this graph is the object traveling the fastest? I would say probably E. It'd be close between C and E, okay? But I think E is steeper, okay? And the only reason I say E is because I recognize that this graph shows me how quickly position is changing. The steeper the line, the faster the position is changing. So the steepest line is the fastest part of the graph, okay? It's not a matter of memorizing, it's just a matter of analyzing what's on my graph, okay? All right, what if I asked you to calculate the total distance traveled? See if you can figure that out. Okay, just using this graph, calculate what the total distance traveled would be. I'll give you a couple minutes before you ask. Okay, who thinks they got it? Okay, what is it? 32 meters. Okay, so here's how we figure that out. In part A, the object moves from a position of 0 to a position of 6 meters. How far does it go? 6 meters. How far does it go here? Doesn't go anywhere, right? It's sitting still there. All right, in part C, it goes from positive 6 to negative 10. How far does it go there? 16 meters. How far does it go in D? 0. Okay, and then between here and there, it goes from negative 10 to 0, so it goes another 10 meters. 10 plus 16 is 26, plus 6 is 32. Okay, so that involves having to do a couple of things. We have to recognize when the object is moving and when it isn't. So obviously in B and D, it's not moving. Okay, and then figure out how far does it go in each part. Okay, which is final position minus initial position. And we just add them all together because distance doesn't care whether you go forward or backward, just how far do you go. That's why we just added them together. It didn't matter whether it was forward or backward. Okay, assuming that this all ends at 18 seconds, what's the average speed of the object? Okay, we want to calculate average speed. We need total distance divided by total time. We already calculated the total distance. It was 32 meters. Total time is 18 seconds. What are we looking at there? 1.8 something? Was it 1.87?
It's 1.7.
1.7, okay. So 1.8 meters per second. There's my average speed. Okay, now that's actually easier than the garbage truck question. But that's kind of what the garbage truck question would have looked like if we'd have drawn a position time graph on it. It would have shown it doing different things. Okay, it's just in this case we have it all laid out for us, and we don't have to figure out all the individual parts as in the same way. that would be a very typical question and that might give you on a test. It wouldn't take you very long to do, right? It seems like when you first look at the graph and first, we'd be presented with the questions, it would seem like a lot of work, but there's really not that much to it, right? I mean, the most difficult math we did there was dividing two numbers, right? The rest of the time we're basically just adding. Okay, questions on how that worked? Okay, sometimes you're going to get a graph that's got curves on it. Okay? On any graph, a curve just means that the rate at which y is changing is not constant. Okay, that's all it means. Because if it's a straight line, okay, if I have a graph that looks like this, and it's a nice straight line, it means that y is changing at a constant rate over x. If I get a curve, it means the rate at which y is changing is not linear or not constant. Okay? So in a graph like this, okay, we know that the position, the rate at which the position is changing, is actually increasing. Okay? In other words, this object is doing what? At least here in part A. It's accelerating. Right? It's going faster and faster, just like that train question we dealt with right at the beginning. Right? In the first 2 seconds, it only went that far. In the next 2 seconds, it went further. The next 2 seconds, even further. The next 2 seconds, even further. It's going faster and faster. Okay? Now, the other way that we could kind of prove that is this. I'm going to explain to you the only thing I understood in university calculus. It was the first day. It was very discouraging after that. Okay? To a mathematician, a curve is an infinitely large number of infinitely small straight lines strung together. Okay? So it would be like if you looked at a picture online that was really low resolution. What would you see in it? Pixels, right? You'd see all the little individual squares. That's how a computer makes curved edges. It just uses squares. If the squares are really small, we can't see them and we go, oh, that's a really high definition picture. Okay? That's how televisions work as well. Okay? The pixels are so small that we can't see them. Right? But if you're watching a YouTube video at like 480, you can see all the little boxes. Okay? Well, to a mathematician, this curve is a whole bunch of little boxes. Okay? And they get steeper and steeper and steeper. That's what makes up the curve. Everybody kind of follow me on that? Okay. So in part A, we've got a whole bunch of little lines that are getting steeper and steeper and steeper. That means the object's going faster and faster and faster, okay? Because the rate at which it's changing its position is getting higher and higher. All right, so for part A, the object is accelerating. But once it gets to here, that changes. Now what does the line start to do? Instead of getting steeper, it starts to get flatter. Yeah. Okay. Here it's speeding up, speeding up, speeding up, and now it's getting slower and slower. In fact, there's an instant at the very top where it is stopped. Okay? So, like if I was showing you just the top of this line and I drew a tangent to that line, it would be horizontal. There'd be a moment there, an instant at least, where the object was stopped. Okay? Now, after we get to that point, what happens to the line? It starts to get steeper. Right? It goes faster and faster until it gets to about here. And then, what starts happening to the line? It starts getting flatter again. What is this a graph of? Somebody throwing a marker up in here. Okay. Part A is the part where I'm throwing the marker. I'm making it go faster and faster. And as soon as it leaves my hand, gravity starts to slow it down, slow it down. So here's the part where it's just gravity between here and here. Gravity slows it down, slows it down, slows it down, stops it for an instant at the top, and then accelerates it back to my hand. That's why the two halves of that are exactly mirror images of each other. Because in both parts, gravity is what's doing the accelerating. Okay? And then this part is the catch. Okay? I catch it, I slow it down, I bring it to a stop. Okay? I would never ask that on a test. I would never put a graph on a test and say, tell me exactly what was happening. Okay? I might ask you to describe, this part's accelerating, that part's accelerating. I'd ask you to do that, but I'd never say, what was it? Because that's really not fair. All right, questions on that one? Okay, let's look at a few position versus time graphs here. That's velocity versus time. Oh, that was position. Okay, so let's have you guys try this question here. We got a bus that's making a trip according to this position versus time graph, so the one you see on the right there. Okay, I want you to calculate the average velocity of the bus, okay, during each of the labeled segments. So that would be A, B, and C, okay, and over the whole trip. Okay, so it might be hard to read here, so just for clarification, man, is it ever hard to read? This would be about 25. Okay, this would be 33. So the highest point would be 33. Okay, and this one here is 28. It's right on the line, so we'll say it's 28. Okay. All right, give that one a try. I'll give you a couple minutes on that and walk through it together. Okay, so this one's pretty straightforward. Okay, if we want to calculate the velocity in each section, okay, so for part A, so the velocity in section A is simply going to be the displacement divided by the time. So that's going to be 25 over 1. Okay, so that's simply going to be 25 kilometers per hour. Okay, the velocity for part B is going to be our displacement over time, but we're going to go final position minus initial position divided by time. So that'll be 33 minus 25. Okay, and that takes place over 1.25 hours. Okay, so 1.25 hours. Okay, so we do that. I don't know if it comes out to exactly 6.4, but it should be close to that. 33 minus 25. God, I can't believe I typed that in. Divided by 1.25. Okay, 6.4. Okay, kilometers per hour, and that's positive. Okay, and then for part C, okay, same thing, final position minus initial position over time, so that'll be 28, okay, minus 33, okay, over, that's another 1.25 hours, because it goes to 3.5. Okay, so we're gonna have 5 over 1.25, which should give us 4.8 kilometers per hour, or something close to it, but it'll be negative. Okay, so 28 minus 33 divided by 1.25, okay, negative 4. Okay, so I must have got a number slightly different off that graph than I did the first time. Okay, and then for our total, okay, total displacement we said was 28, so it probably didn't come out to exactly 7.7. Okay, 28 over 3.5. Okay, so 8 kilometers per hour. All right, is that ringing a bell from last year? Okay, I would have had you do stuff like that in science 10. In fact, I may have had you do exactly this question at some point in science 10, so nothing really new there. All right, tomorrow there will be a quiz. I will post it tonight after school. So between 3:20 and 3:30, it'll appear on Google Classroom. Okay, try the practice quiz, and then tomorrow's going to be pretty much the same thing, if not exactly the same thing. Okay, we'll just see how that goes. okay? But know that that's gonna happen, take 5 or 10 minutes tonight. It's gonna be on V equals D over T, might possibly have a position time graph, okay, like this one. All right, I'll have you guys pack up, we're gonna come around and wipe off all those desks.